Thank you for the introduction, Davide. So my name is Håkon Norén, and I am a PhD student at the Norwegian University of Science and Technology. And I will talk about how you can learn Hamiltonian systems by using mono-implicit Runge Kutta methods in combination with Hamiltonian neural networks. And I should emphasize that this is joint work with Elena Celedoni, my supervisor, and Sølve Eidnes, which is my co-supervisor. So the problem that we consider, it's an inverse ODE problem. So this is an ODE, and instead of considering the standard initial value problem where you have an initial value and you know the vector field and you want to compute discrete solutions in time, we instead consider that we have this, we assume that we know the discrete solutions exactly, but we don't know the vector field. And what we want to do is we want to find an approximation to the vector field by using some parameters theta by exploiting the information of these discrete samples. And an example could be the four-dimensional double pendulum problem formulated on as a canonical Hamiltonian system, where we assume that we have 10 samples, and we want to find the vector field that gives rise to these points in the flow. Such that ideally, when we integrate it, we will obtain a trajectory that tracks these points, and ideally we would want to interpolate between the points, and even better if we could extrapolate after the end points in time. That would be even better. So why would this be interesting? It could be interesting in cases where you have you want to model systems where it's difficult to find the analytical expression for the vector field, but it might be easy to monitor the system and to collect data. And two use cases could be control of autonomous systems, such as quadrotors, where they use a port Hamiltonian formulation, which is a Hamiltonian system that includes dissipation and forcing terms. And similarly, you can also use it for more industrial applications. So a Hamiltonian system, a canonical Hamiltonian system, looks like this, where h is a scalar function, our Hamiltonian, and it's ubiquitous in physics, and it's derived from classical mechanics as the sum of kinetic and potential energy, and such systems are energy preserving, since we see that the time derivative of the Hamiltonian is 0 due to the antisymmetry of this canonical structure matrix J. It is also symplectic, since the flow map of the system satisfies this property here. And in the setting for solving inverse problems, we will use the assumption that our data comes from a Hamiltonian system, and we'll follow the idea of Hamiltonian neural networks that was first presented by Graidanus in 2019. And we will structure the neural network such that it will always form a Hamiltonian system. And we can compute the gradient by automatic differentiation. And this is the neural networks we use. It's standard feed-forward neural networks, which is a combination of affine and element-wise nonlinear transformations. So nothing really interesting here. And what we end up with, there are many ways to formulate these optimization problems, but we'll consider just taking a step with a numerical method, and we want to adjust the vector field, our Hamiltonian neural network, such that the point that we arrive at is as close as possible to the data that we observe, this y evaluated in Tn plus 1, or the pointwise observation. So in total, we have some observations that we assume come from a Hamiltonian system. We use a neural network that is structured as a Hamiltonian by construction, and we choose an integration method which we will discuss in greater detail. And we end up with this loss function. So if we consider the implicit midpoint method with a rather large step size, we would end up with the following loss function. And yeah, if we train it, you see that it breaks down. It doesn't work that well. So let's try to do a rather superficial analysis to try to understand why this happens and what we can do to remedy this breakdown. So, inspired by backwards error analysis, we can consider the loss function that we have, and we can ask the question, what vector field would satisfy this condition exactly? So here we change the notation from the point that we know to the flow in time, the exact flow. And we can see that the vector field, which we now will call f subscript h, which in some cases are called the inverse modified vector field, it is the vector field that satisfies the following condition. And if we know, let's now assume that we know the vector field and we know the numerical method that we use, the large phi, we can derive this f subscript h by Taylor expansions. It's not too hard to show that this inverse modified vector field, f subscript h, it agrees with the original or the underlying true vector field with a leading order error term, h to the power of p, if the numerical integrator is of order p. So if we have a numerical integrator that is of higher order, we will have a greater agreement with the inverse modified vector field, which is the vector field that gives us zero loss in the optimization problem. So just as an example, if we consider the implicit midpoint method, it's possible to derive the inverse modified vector field on the following form. So with this motivation, let us consider higher order methods, because if we can use higher order methods, we would have a more accurate condition in our learning problem. So as we all know, this is the form of Runge-Kutta methods for an autonomous ODE with S stages. And the problem is that these methods might be implicit in their stages, which means that we might have to solve a large nonlinear system for every training step that we take on our neural network. And we don't want to do that because we might have to backpropagate through a nonlinear solver. So we want to avoid doing this, but at the same time we want to find the Runge-Kutta methods of higher order. And one solution to this is to consider the class of mono implicit Runge-Kutta methods that were introduced in the 80s, which are a special class, a subclass of Runge-Kutta methods, where we introduce coefficient vector v and a strictly lower triangular matrix D, and we reformulate our coefficient matrix A to be a product of to be a sum of the outer product of V and B and this strictly lower triangular matrix. And what we can then see is that it's possible to rewrite the stages of the Runge-Kutta method on the following form. So we can separate out this outer product, and since the end step is defined as it is, we can actually inject the difference between the final point and the current point yn that we're standing at. And the nice thing now is that we know ytn and ytn plus 1. So we can actually inject these points into the computation of our stage. And since the D matrix is strictly lower triangular, we end up with an explicit procedure to compute the stages, and which gives us an explicit Runge-Kutta scheme in total. And it's possible, it's quite trivial to show that the modification of the method by injecting the known points it leaves you with a method that is of the same order as the original method. And these methods, the Mirk methods, they're a larger class than the explicit Runge Kutta methods when we consider explicit methods for initial value problems, because we are able to, we can include the this part here, not just the strictly lower triangular part. So we have greater freedom to choose methods, and we can have higher order with fewer stages, which again means that you have more computationally efficient methods. They can be symmetric and they can be symplectic, but maximally of order 2, which we've shown in our previous work. And they are usually displayed with a butcher tableau on the following form. And this is just a illustration to show the relation between the different methods and to show that this class of Mirk methods is much larger than the ERK or the explicit methods. And they include symmetric methods and symplectic methods. And in fact, the symmetric and symplectic method of highest order is the midpoint method, with, if you want the method with fewest stages. So here is some optimal methods that are derived by Muir in 1999, up to from order 3 to 6. The butcher tableau of these methods. So let's try to use these methods to learn Hamiltonian systems from data and see how it goes. We will still consider the double pendulum problem, which is known to be chaotic. So if you perturb the initial value, you will end up with a flow that is quite different from the unperturbed one. We'll consider an increasing number of points. And we will do interpolation and extrapolation when we integrate over the learned vector field. So we start up with a implicit midpoint method, and we see that it doesn't perform too well. But we see that when we increase the order, we get an increasing correspondence with the underlying, with the true trajectory when we integrate the known vector field. So in total, we see that we are able to get accurate interpolation and extrapolation when we use a method of high enough order. It's quite surprising that you're able to get such accurate results, even though you only have 10 points with quite a large step size in between them. So this seemed to indicate, without a very strict and formal analysis, this seemed to indicate that the order of the methods are important. And we know that the Mirk2 method is symplectic, but in these cases, at least with large step sizes, the order seems to be more important than if the method is symplectic, at least for these experiments. So with that, I would like to thank you for the attention. And these are my references. Yeah.
Okay, thank you, Håkon. Are there questions for Håkon?
I have a question.
Yes.
I can understand it. So, thanks for the talk. I wonder if this modified row Kutta integrator that you're using is symplectic or not, or are they coming from the discretization of some variation of principle as well? Like a lot of other symplectic.
So your first question considered the symplecticity of the methods, and so what we have shown is that if you enforce both the structure of the mono-implicit Runge Kutta methods and the symplectic, like there is an equation for the coefficients. If you want it to be symplectic, you are only able to get order 2. So you can find a mono-implicit method, but it's maximally of order 2, and the method with least the minimal number of stages is the implicit midpoint method.
So in that case, it's not explicit. It's for higher order integrators.
Yeah, I mean in the classical initial value problem, it's not explicit. It's implicit in only in the next time step. So we don't have to solve a system for every stage, only for the next point. That was maybe not so well explained, but yeah. When it comes to your question about if it is derived from variational principles, I'm not aware if that is the case, so I don't think so.
I think if this is not symplectic for higher order, maybe it's not derived from the variational principle. Because by construction, then it has to be symplectic.
Okay, yeah, that I'm not aware of. I don't know, basically. Yeah.
We can talk about it later.
Yeah.
Thank you.
There was another question.
Yeah, so I have a very naive question. If you see in the future of using a methodology for optimal control problems as well, instead of just learning the ODE, also some optimization problem involving the ODE as well.
I mean, I think, as I said in the introduction, that the use cases they could be quite interesting when you consider control problems. But I haven't thought about how you would, if you want to do control problems, what kind of properties you would want to have from a numerical method in that case. So if you have any ideas about that, it would be interesting to.
Yeah, so you can also write a Hamiltonian for the optimal control problem. So in that sense, if you start from the optimality condition, you have basically a Hamiltonian ODE plus some constraints. So you can learn something that will solve the optimality conditions, for instance. I was thinking, but solving the global control problem is more difficult, of course. So that was why I was asking.
Yeah, no, it's I don't know basically, but it sounds like an interesting problem. So yeah, would be interesting to discuss with you later.
Thank you.
Yeah. Hi. Thanks for the talk. I have a question on. So there was this paper by the DeepMind guys, Peter Battaglia and co. From 2019 on using high order integrators for different tasks, right? So for Hamiltonian system, but also non-Hamiltonian. And so they showed that indeed, so high order integrators are better on Hamiltonian systems, but on non-Hamiltonian systems, eventually lower order integrators are better. Do you have any insights on this, or do you know of any follow-up work on this?
No, I don't. But for this type of problems, I've tried. I mean, there is nothing in these problems that says you have to consider Hamiltonian problems. If you go from using Hamiltonian neural networks to like a general vector field, modeling it directly with a neural network, and I haven't done very systematic experiments with non-Hamiltonian problems, but I have not found any results that seems to suggest that there is a difference in whether the order matters between non-Hamiltonian systems and Hamiltonian systems. But
okay.
Yeah.
Okay. Thank you.
Okay, let's thank Håkon again. And now is the turn of Marta Girardelli.
Davide, com'è che fa? Schiaccio qua.
Yeah.
Ok.
Okay, so now is the turn of Marta Girardelli, and she's talking about optimization via conformal Hamiltonian systems on manifolds. So, please, Marta.
Hello, thanks, Davide. I am also a PhD student as Håkon in Trondheim at NTNU. And today I would like to present you the work I've been doing in the past couple of months, which is to develop methods in order to perform optimizations on manifolds. And these methods are defined using a conformal Hamiltonian system. So we start from the very beginning. So we have a function f, which is defined on a manifold, and we want to find its minimum or one of its minimum. And what is usually used in this setting are gradient descent algorithms, or they are a choice. In particular, they are widely chosen because they only require a first order information of f in a point, so the gradient, because they use the negative direction of the gradient in a point, and hence they are very easy to implement, and this is why they are widely used in machine and deep learning, because one has to deal with large amount of data, and having the algorithm easy helps. The only, let's say, drawback they have is that they converge only linearly. So for what concerns the Euclidean space, there have been attempts and methods have been written out that are some accelerated versions of the usual gradient descent methods. And I want to mention you one of them, which is, you may know it, is the Pauliak's heavy ball method or classical momentum. And the reason why I want to mention it to you is that because it can also be seen as the discretization of a conformal Hamiltonian system. And because the idea I have is to consider the corresponding conformal Hamiltonian system, but when f is defined on a manifold and not in the Euclidean space. So the assumptions we are going to have are that still the manifold is, we see it as embedded in an Euclidean space with some coordinates q, and we enforce this q to satisfy these points, to satisfy some constraints so that the points belong to the manifold. And then you will see capital J in later on, it's just the Jacobian of these constraints. And then we enforce these constraints via Lagrange multipliers, lambda. And we consider f, we see it as the potential energy of a mechanical system. So this potential energy just depends on the positions q. And we consider also the kinetic energy, a kinetic energy. What's important is that it just depends on the momentum p, and in this case I've chosen the usual one. So summing them up, we obtain the total energy of the system, also known as the Hamiltonian function. And it is separable because we can separate what depends on q and what depends on p, and it is also associated with a vector field, which is the one you see in this system. And the properties of this system is that it preserves the energy, so h is conserved, and the flow of this system is symplectic. Just a little note, the function h results being defined on the cotangent bundle of the manifold M on which the function f is defined on. But here we have a problem because as the energy is preserved, then if we start on a point and we evolve the system from that point, then we remain on the level set of h on which that point belongs. But what we want to achieve is a minimizer of f, and we want to do it by achieving a minimizer of h, the Hamiltonian, because then if we find a minimizer q star p star, since h is separable, then we also have found a minimizer for f. So what we have to do is to dissipate energy. So we introduce a dissipation term, which is the one you see in blue. So, and we introduce it with together with a parameter gamma, which is called the parameter of dissipation, and it regulates how much the energy is dissipated. It's a positive term, and systems of this kind are called conformal Hamiltonian. And here I've written the definition of what a conformal Hamiltonian system is. First of all, we need to be on a manifold, a symplectic manifold, and we require it to be exact, meaning that the omega 2 form is not just symplectic, it's not just closed, but it is also exact, so it can be rewritten as the differential of a one form, in this case theta. And then we can define a conformal vector field and a conformal flow, as you see here. So a vector field is conformal with respect to the parameter c. If the Lie derivative with respect to x of the 2 form is c times the 2 form of omega, and a similar definition we have it for the flow, for which we consider instead the pullback. And so now we want to find a solution of this system, and we produce an approximation of it. To recover it, we split the system in two parts. Basically, we go back to the conservative part, and then we consider the dissipative part separately, so that their sum is the total system. And for the conservative flow, we approximate it with the Rattle scheme, which is the one you see there in the system. With the first 3 lines, basically, we compute the next position and the next momentum, and the next position Q, thanks to the third equation, already stays on the manifold M. But P, it's not in the tangent space of the point we reach, so we need to add a projection of it onto the tangent space, which are the last 2 lines. This system is symplectic, symmetric, and convergent of order 2. And for what concerns the dissipative part of the system, that can be solved exactly. It's just Q remains the same, and the momentum are multiplied by an exponential. And composing these two flows, we get the flow of the whole system, and this is also known as splitting method. We consider 2 of them. The first one is of first order, so we just do a step in time. H is the step size, a step in time with the dissipative flow, and then one with the conservative flow. Whereas I also consider the second order scheme, which is also symmetric. So we do half a step with a method, then a full step with the other one, and then again half a step with the first we've considered. And the result is that the methods, the scheme we obtain for the first one, as we might have wished to prove, is convergent of order 1. It is conformal symplectic with parameter depending on gamma and h is the exponential. And the second one, as we might expect, is of order 2, convergent of order 2. It is symmetric, and it is conformal symplectic with the same parameter as the one above. I also have tried to formulate an adaptive routine, adaptive step-side routine, and I have done it following an idea which I found in a paper, which was suitable for it proposed a method for adapting the step size that is suitable in optimization. So it doesn't aim at having a very accurate trajectory, but the aim is to reach a minimizer in the fastest way possible. So what we need to do is to compute the solution with 2 methods, and what is important is that one is of a higher order of the other one, and I've just formulated so that we can compute their distance, the distance of the solutions, and then according to this distance we computed the next time step using this formula you see here, where there are also other parameters. In particular, we have theta and r. Theta basically allows you to control how much you let h change from a step to the next, and r instead is the desired error you would like to have in between the 2 solutions. Yes. And a little note, as we've seen, the previous methods were conformal symplectic, but the parameter was depending on the step size. So if we change it, the method is no longer conformal symplectic. I have tried to apply these methods to an example, just one, because I didn't have time to go further with other examples. And I've just considered an easy one, a minimization of a function on a sphere. The function is the one you see there, U transpose AU. And basically finding its minimum gives you the minimum eigenvalue of the matrix A, which has to be symmetric, and we enforce U to belongs to the unit sphere. So in my tests, I build A randomly, but I keep fixed its minimum and maximum eigenvalue, because it turns out that the results I can somehow get some conclusions using according to the difference we have in between these two values, which I've called the I lambda. So it's the interval in which the eigenvalues range. And what I've noticed is that as this interval increases, then we also need a larger dissipation in order to achieve a convergence. But I couldn't find any rule to actually choose a specific one for each case. And then comparing the two splitting methods of order 1 and 2, they work equally well in terms of number of iterations. And whereas the adaptive routine, it allows you to decrease the number of iterations. And then as a general tendency, we can say I could see that smaller, when the eigenvalues, they range in a small interval, then we require more iteration. Here are some plots to show what I've just said. So from the first to the last, the interval of range of the eigenvalues, it is increased. And as you see in the title, the last value is gamma, the dissipation. And also that one is increasing. And then you see in blue, it's just the usual, it's the first order scheme with fixed time step equal to 0.1. And comparing it with the green one, which is the adaptive version starting from that step size. You can see in the legend that there are the number of iterations, and using the adaptive routine, especially when the interval is small, allows you to reduce the amount of iterations. And in orange, I've just tried for each particular case to plot the fixed step size method, but enlarging the step size as much as possible. But this can be done, you have to do it basically for each. Anytime that you choose H, you go on and try. I have also compared these results with what comes out when using a usual gradient descent method, which is the one you see here. I've studied it a little bit, and because I wanted to find a proper H, because this does not converge for all H, for all the step size. And I found out that if you choose a truncation of this ratio, then you get an H that allows you to reach convergence, and in a reasonable amount of iterations. So meaning that it's not the optimal, but it's not even that far from the best you can reach. Here are the results, and basically as you can just have a look at the number of iterations, and basically the gradient descent and the adaptive routine, they are comparable, or sometimes the adaptive scheme is even better. So for what concerns this example, the schemes I have formulated, they seem to be a valid alternative to the usual gradient descent method. And so to summarize, I have formulated schemes that are conformal symplectic, and they are suitable to work in the manifold setting. And they are a valid alternative to the gradient descent, at least in the example that I have considered. What I would like to do is to consider other examples, in particular involving more interesting compact manifolds, such as the orthogonal group or the Stiefel manifold. And what I would like to do also is to consider problems that are more related to the field of machine learning and deep learning. And then I would be interested in using another kinetic energy instead of the usual one. In particular, I would like to try with the relativistic kinetic energy. Using that one means that also the very first system we've seen will be different. And so I would like to see what comes out if I can build the system first of all, and then if by discretizing it I get to a method which is conformal, symplectic or not. And yeah, this is it. So I thank you very much for coming, and yeah.
Questions for Marta? Yes.
So you had a higher order scheme for the for discretizing your flow that you are approximating to perform the optimization, and on the other hand, Lee Trotter, right? Just the first order.
Yeah. So we have.
Yes. Yeah,
so
yes.
first of all, this system here is split in two parts. So basically the blue one is alone, and then the rest. The rest is the conservative system, and the blue is the dissipative system.
Yeah,
I solved these two separately, and the first one, this one, the conservative part is solved with the Rattle scheme, which is of order 2.
Yes, and but this, does it mean that the convergence to the minimum is also of higher order? So what's kind of the motivation of trying to have a higher order discretization of this flow? Does that directly translate to...
No, can you repeat the question?
So does the order of the scheme here translate to the order in of convergence
of
speeds
the total scheme
to the minimum? Yeah.
I have to say yes, because the proof I've used the proof of this theorem here, it follows exactly the proof of the Rattle scheme. So I've proved the convergence of the methods, the complete method. Following is just a modification of the proof of the Rattle scheme. Being able to prove it in another way, maybe you can...
yeah, okay, so I mean, I see that it's a second order discretization of the flow, but does it also mean that the convergence to the optimum is of second order? Or
that one I don't know how to answer, because it's something that I haven't checked.
Okay.
If I have to be honest. Yeah.
Okay, thank you.
Thank you for the question.
Okay. Any other question? Yeah, I have one, and maybe in the meantime you can try to set up the link. So this addition of minus gamma p is very convenient and nice, because you have an exact solution, right, of the dissipative part.
Yes.
But have you considered maybe adding something that is not just linear in P, but maybe depending on Q?
Actually, it turns out that if we want the system to be conformal symplectic, then that's the only choice. Mm-hmm. Because they are all, I've seen the definitions, and I've seen that you can always choose the coordinates so that the I think what you can do is maybe do a dissipation just on Q, because to get a conformal Hamiltonian system, then you have that it depends just on one of the two variables.
Okay.
And then depending on how you choose the coordinates is either one or the other one.
I guess my question was more like why one needs to restrict to conformal systems if the dissipation is the only purpose. But I can see why it's very convenient
yeah,
to do not have.
It is easy to not have more complicated systems. But other than that, I've started with the idea of considering conformal Hamiltonian systems, so I didn't consider others.
Okay, great. Thank you very much.
Thank
Let's
you.
thank Marta again.